So now the goal is to prove the theory. So here is what we need is the existence of an increasing process such that m squared minus this process is a local martingale. Here is a lemma that we proved. And just a well, okay, we just proved it. Now back to the proof of the theorem. First, assume that our martingale is bounded. Our local martingale is bounded, and there is no difference with local or non-local. So assume first M is bounded. Okay, maybe it's a bit too much to assume the boundedness on the whole half line, but let us assume it's bounded on a segment. Okay, and work on this segment. Then it follows from lemma what do we know? We know that, where is lemma? Here is lemma. We know that this expectation, the expectation of the square tends to 0. We can apply, all these guys are continuous martingales, so we can apply Dub's maximal inequality. And what we also know is that when both Nm tends to infinity, then the expectation of the maximum of 0 no t of 0 capital T of this also tends to 0, right? Because it's estimated by that from above with a factor of 4. This is Dub's maximal inequality in L2. Okay, good. Now, okay, given a sequence of nested partitions, like in this theorem, what we can now do, we can now find a subsequence and 1 and 2, etc., such that, say, the first expectation is, when the minimum of them is n1, this expectation is less than 1/2. When the minimum is n2, the expectation is less than 1/4. The expectation such that for any m greater than nk, the expectation of this maximum over 0t xt nk minus xtm, okay, just absolute value, it's bounded by the expectation of the second moment, is less than 1 over 2k. Okay. I can just choose them consequently large enough. And in particular, it means that the expectation of a sum over all k of this maxima xt and k minus xt k plus 1 is less than 1. Less than 1 here. In particular, it's finite. Of course, no mind what is there, just some constant. And in particular, this is finite almost surely, which means that they converge as continuous functions. Okay, T0. So almost surely I can find such a limit. Almost surely this exists. Again, on a negligible set, I redefine everything by nice continuous functions, identical zeros. Okay, good. So what do I know about xt? So we know first, what should I know? First, I should know that this is a martingale. Why? Remember, we are in a bounded case, right? So to check that something is a martingale, basically what I need to check is to check that the expectation of xt, whatever z, is the expectation of xtz for any z fxsz for any z bounded fs measurable. And this is something in which this is an identity in which I can easily pass to the limit. I mean, the limit of martingales, if there are no issues with infinities, with possible fails of dominated convergence, then the limit of martingales is a martingale again. Okay? Second, what we know is that m t squared minus xt. So this xt is a candidate for m squared minus quadratic variation. So I would like to claim that this is an increasing process. Maybe this claim deserves to be made even before, even somewhere here, before before writing what the lemma is. Why? Just because okay, this is an identity. When you what I claim is that minus 2xt is an increasing process, right? It should be 2. What I'm claiming is that this, this is just a trivial computation. So think about, okay, let me just write what m squared minus 2xtn is. I'm saying is that this is sum of squares, m tj t minus m tj minus 1 t squared. Does it look okay? Think, say, about t capital, about the right end. Then here Okay, this is the identity. I already wrote it for the Brownian motion. It's exactly the same identity. So remember when I computed the integral b dB, right? So what we had exactly these sums. And what I told you is that if you subtract the quadratic variation, which is that, what you have is just the square of your process. It's just linear algebra identity, and we already saw it. So what I'm saying is that this is an increasing process for any given n, and so the limit is also an increasing process. So yet again, how this works. I'm just saying you, okay, I would like to consider this process. But the reason I didn't tell it to you before, the reason is that actually this is a good candidate. This difference is an increasing process by some linear algebra. And also, this is a martingale. So this is a very good candidate. And the whole battle is to prove that there is some subsequential limit, which is done here. Okay, so now this is an increasing process. This is a martingale. This is exactly what we need. Moreover, so for a while this is on a finite interval, but moreover, we also have this identity along this particular subsequence of partitions. We also have the identity mm T capital is the limit when k tends to 0 of these sums. 1 to p and k, and tj is tj minus 1 squared, and k and k. So basically on a finite interval, on a finite segment, and for bounded martingales, we're already done. So that's it. This lemma makes the job. Yeah. Along the subsequence. Okay, good. Now that's just formalities. What else should be said? First, let us, okay, bottom line. For m bounded on 0t, we have constructed mt again on 0t is wanted. Now first, let us still work with bounded, with martingales which are bounded on each finite segment. So now consider enlarging intervals 0, 1, 0, 2, 0, 3, etc. So assume that our MT is locally bounded, is bounded on any finite segment. And just run this construction for each of these intervals. Then on each of these intervals, we have some process, right? We know that in the theorem, it cannot be that there are two different guys here. We know the uniqueness statement, right? And uniqueness statement, it holds on any interval. So, and now that these processes must agree due to uniqueness. Okay. So we know how to proceed on each of the finite segments, and we know that the construction is consistent because otherwise on some of the segments we would have two different quadratic variations, which, I mean, two different processes that find this, which is impossible. Okay, they're consistent, so we have the whole construction on the half-life. Moreover, in fact, we know that it does not depend, that what we did here, we have chosen we chose some subsequence of nks, right? But in fact, we know that the whole limit exists. Why exists? Why? Just because, okay, from any sequence you can take a subsequence such that the limit exists, and it is always the same because of the uniqueness. Okay. Moreover, the limit exists and the same for all sequences. Again, of partitions. Again, by uniqueness. So if our martingales are locally bounded, if this holds on any segment, then there is nothing to do. Okay, we already there. Okay, some technicalities, some formalities, I would say, is that, I mean, about what to do in the general case. Okay, general case. What to do in the general case? Just consider appropriate stopping times. So just consider tau n be the infimum of all times. I mean, infimum, the time when the martingale, the local martingale reaches the level n. Okay, and stop it there. And denote Tn T This is, I mean, a pretty standard idea. I mean, you have something for bounded functions, now you extend for unbounded. So we have this object, m. Okay, just because this is the result of the previous construction. And note that, again, by uniqueness, implies that they agree with each other. That this is the same as the next one, or the previous one, if say m less than m and t less than tau n. Why? Okay, I think we're all a bit tired to check it formally, just an exercise. I mean, I can write on the blackboard. What? Oh, yeah, indeed. Yeah. Just because if you think about the process m n t squared minus m t then this is the same as that, and therefore it's a local martingale. And we know that there is only one increasing process that we can subtract from there or from the square such that we have a local martingale. So they agree with each other, so we can define MM just as a limit. Okay. For any given time, for any omega starting from some moment, from some number, all these guys are the same. Okay, so we have a process, and okay, this is a trivial check. This is an adaptive process. This is increasing, and that m squared minus mmt is a local martingale. So we indeed constructed what we wanted. And the last comment about this identity, here in this identity, so what we also know is, well, we know this identity for any of the stopped processes. So imagine you could put here Tn, tau n. So you know this identity, and then you know that almost surely this tau n from some point exceeds t. So that the probability that it somehow infers what's going on tends to 0. So because of that you have identity in probability. So you first say, okay, let me try to figure out what is the probability that these guys differ by 100. I would like by 1%. I would like to prove that this probability is small, say smaller than whatever, than some epsilon. Then I say, okay, first let me find a sequence. Let me find some bad events of total probability epsilon over 2, such that tau n with some greater n is less than t, and drop all these events away. I mean, I'm not interested in that. In what the rest, I know that these two guys become closer than 1% with probability less than epsilon over 2, provided this n is big enough. So what I'm saying is that if you have this for each of tau n's, and you know that tau n tends to infinity, then you easily conclude that the probability is still there. Okay, anyway, this is all a sort of formalities, as I already said. The core part is actually in the lemma and in this construction. Okay. So the bottom line is that, okay, now for any local martingale, we have a very nice process, which is an increasing one, defined uniquely. And, well, moreover, we know that this is a limit of increments, sum of increments squared. Okay, good. And now, some concluding remarks. Not many, but still something to do. Are there any questions, by the way? I mean, mostly about the general structure of the proof. Do you see how it works? I mean, it was rather complicated with many details, right? First, do not think about the very end, how to pass from, the bounded case to unbounded. Okay, just, you know, provided it works, you can reconstruct it as usual. So you are not always sure it works, but if it works, then it should be an easy way to reconstruct it from formal statements. Okay, then in the bounded case, what we know, we need some clue how to construct this MM. So instead of constructing this process, what we are doing, we are constructing this martingale. How to construct this martingale? We say, okay, let me make an educated guess. Let me write a sort of an approximation. Why this is a proper educated guess? Okay, it's already erased, but this is a computation we had for the Brownian motion. And then basically what we need to prove, we need to prove that there is a limit of these guys when partitions refine. Okay, how to prove it? We need to prove a sort of a Cauchy statement. Here is the Cauchy statement. Okay. Good. Now remarks. Where is the theorem? Here is the theorem. Okay, remarks. First, in fact, I already used something like that in the proof and even tried, to write a formal line which proves it. So let tau be stopping time. And m tau be m t min tau. Then tau t and t minimum tau. Okay, the taking of quadratic variance commutes with stopping the martingale. Nothing deep. Exercise, see the proof when basically I argued, well, I tried to argue for concrete stopping times tau n, which is the moment when it hits the level n. Okay, second, this is 0. What I mean is 0 almost surely, if and only if t is 0 sure. Not in a concrete sample, but it vanishes on all the events if and only if the martingale itself vanishes. Why? It should be something trivial, be third. Okay, just yeah. First, this is not completely correct. So in the whole discussion I had, I never commented on the role of M naught. For simplicity, you can always assume that M naught is 0. Okay, martingale starts at some value. Still, there is some tricky issue if the starting point has no first moment, for instance. If the expectation of M naught is unbounded, so you need a bit more technicalities, but this is not the case. So, this is not a big issue. What I mean here is that, okay, provided M naught is then, okay, if we are able to apply, if this is a true martingale, if, say, M is bounded, then optional stopping just give you that the expectation of mt squared minus mmt is 0 and you are done. Okay, so if you know that the quadratic variation is 0, then you know that the expectation of mt squared is 0 and you are done. In general, consider stopping times when you hit some level, say m, argue for this martingale, and then say that, okay, I know that this expectation is 0, and now I can pass to the limit using Fatou lemma. Okay, just trivial remarks. A slightly more general remark that also is needed for the future construction. So let me call it proposition. And this is last for today. Somehow you can answer, well, a natural question that might be asked is, okay, in this theorem we deal with local martingales. And I tried to explain why it's important to enlarge the class of martingales to consider a slightly more general process. But then, okay, what can be said about the whole construction if this is a real martingale? Other way around, what can be said about this if I know that this process is a proper martingale, not local one? Okay. In the assumptions, theorem, and again, provided that m0 is 0, the following two conditions are equivalent. The first condition is that mt is a true martingale and it is an L2. Again, remember that the first does not follow from the second. There are two assumptions. And on the right, the assumption is, the condition is that the expectation of the quadratic variance is finite for any t. And moreover, if it happens, if we are in such a good situation, moreover, in this case, this process is a true martingale. By the way, note that it might happen that, say, this local martingale is an L2. This holds, but this does not. So in general, what you should think about is that, okay, I have a nice process, and well, I would like to apply optional stopping to here. So if everything works, then the expectation of m squared should be just the expectation of the quadratic variation. Okay? But if you are in a local martingale setup, then optional stopping not always works. And in particular, it might happen that, that this is finite, but this is infinite. The very first example we had with this Brownian motion stopped at the level -1, as far as I understand, provides a counterexample. Or an example to such a situation. Okay, so this is 2 lines to prove. Now, yeah. Well, maybe not 2, but yeah. This is an easy statement. Everything hard for today is already past. It's good news. Okay, proof. So from left to right, what should I do? Okay, let me well, I would like to estimate this. Okay, so I introduce the stopping time, which is an infimum of OT, such that the quadratic variation is big. Okay, before this time I know the quadratic variation is bounded. Okay, and then, okay, what I'm saying is that if I just think about this process, which is a local martingale, then I know that the first one well, what do I know here? Okay, it's less than m less than supremum of m s squared 0t. That's what I know about the first one, and this I know to be bounded by m. And by Dub's inequality, what I know is that this is less than wait, what should I say? I'm just here. I just would like to say that this is an L1 omega. Why? Just because the expectation of the supremum is less than 4 expectations by Dubs. So what's the idea? I have a local martingale. I introduce some stopping time. And what I know is that this is still a local martingale, which is now bounded by some random variable in L1. So what I'm saying is that then I know that this is a true martingale. And then in particular, I can apply optional stopping. And well, okay, I know that. What do I know? Now, basically, I would like to pass to the limit as tau n, as n tends to infinity, right? Doesn't anybody follow the question? Everybody is lost already. Well, maybe then okay, maybe a good solution then is as follows. So everybody is tired. Let me, instead of proving this result, I mean, let us then start with this result next time. Let me explain what happened today, because this is of more importance. Okay, so what actually happened today? Remember, we started with some natural constructions of integrals like x dy. What are the natural cases to consider? So the first is when dy is a bounded variation function. Then we have still T's definition, and we know how to do it. The second example was other way around, some nice function db. In this case, we can just take, a formal integration by parts and take it as a definition. Then it was a remark. The remark was that, okay, there is some identity in L2 between the left-hand side and the right-hand side. And because of that, we can extend this definition basically to any L2 progressive process, dB. Okay, good. Then the next logical step was, okay, let us compute some simple example. And the simple example was the Brownian motion itself, BdB. Okay, that's a simple computation which is related to the Brownian to the quadratic variation of the Brownian motion. And okay, it gave us some answer. Somehow an additional term minus t/2 appeared, just popped up automatically. Then you can think, okay, if I would like to play with more general processes, what they could be? Maybe it's good to play with local martingales. Why? Just because if I integrate some process dB, I have a local martingale. Well, just a martingale. Maybe I would like to have them in the game. Okay, good. So, but then, if you think for a while about this computation with BdB, what you need to perform it? Basically, you need the quadratic variance of your new process, right? So you need something instead of your t. I mean, you need to know, I mean, it should something to appear. It should be something to appear. And then, okay, the whole technical story for today was to explain that, okay, whatever local martingale we have, there is such an analog of t. There is such a process which is called the quadratic variation, and it is defined uniquely just by the condition it is increasing, and m squared minus e is emerging. Okay, now it's constructed. Then, well, okay, we have this formal stuff. Then there are some issues with L2 integrability, which are postponed until the next time because everybody is tired. But this is really simple. I mean, we spend twice less time next time, rather than comparing to how it works now. Okay, and then what is the plan for the future? Basically, you now say, okay, let me take some, I would like to define an integral with respect dm, where m is a local martingale. How to proceed? Okay, let me define it for some simple processes, like step processes, with a concrete formula. And then write a sort of an L2 identity in the same way I wrote for something dB. Okay, and then complete by isometry. Still, something should be checked. I mean, it should be checked that on both sides there are complete Hilbert spaces, to make this definition by isometry. But the whole idea of what the object is more or less exactly the same as in the examples we had, provided we already know what the quadratic variation is. Okay, this is the bottom line for today. Okay, good. Questions?